Oh, hello there. Hey guys, what's going on? Memes here. Yes, we're back, and it's gonna be a short one. Why? Because it's a Friday night, and I wouldn't mind doing other things. Dare I attempt to be human? I know, and I still gotta go run and stuff. So, c'est la vie. I mean, I don't speak French. Oh, the deep lore. Where the heck are we? What am I doing? Oh. Discord, operation, order of operations, and stuff like that. Yes, I know, I know. Professional YouTuber. Oh my God. I have no idea how content creators with large followings manage any of this. God, I essentially bought at least like half of it. No, I didn't. I used marketing, and one thing kind of went in there, and again. I I'm very biased. Yes, I spoke about cyclic cosmology, and a lot of people seem to like that. And unless you talk about something that this is the thing, you just use the algorithm. It's actually really good. It seems to be very good at, in my opinion, showing you what you seek, or what will at least get your attention, or of interest, something like that. Sometimes you gotta kind of force yourself to look at different stuff. Okay, where am I? All right. Going to my own little crazy corner of the internet. In the restricted section of the Wolfram Institute Discord. No, no, not copy pasta peace out, everybody. Oh, God. Oh, utterly. No, not the link to the stream itself. We've done that before. And the interesting thing is, again, very deep lore. I often explore dark places of the internet. Why? Because I'm a wickedly evil person. So at least I know that. All right, moving right along. I think that's the thing we needed to share there. Okay, let's go up. We're gonna race through this. We're basically just gonna go through the spherical God Cow stuff, just because it should be a short calculation, and there's actually an interesting spread there. This is something that requires certain data analysis, because especially if you're using, I think, DESI, and then there's like the DESI. They're two different experiments. They're measuring quote unquote dark stuff, basically quote unquote invisible stuff technically. And they both have contribution. I should really learn what this is. It's not like human beings ever confuzzle things together. All right, so I can't call it a spherical God Cow. Let's just, well, where is this? Oh, let's give the we can give the background. We'll play a wee bit of Professor Carolson. I think we do it. Have we done this yet? Oh, I realize I should probably actually share my screen. God, so bad. All right, exactly 35. Here we go. All right, so here's what we're gonna do. Um, let's just treat the Higgs field as a spherical cow. Let's literally just do it that. Okay, it's gonna be a new section. Treating the Higgs. No, we're gonna say boson, because people probably have other things for the Higgs in the Higgs boson as a spherical cow. There we go. It's been said. Been said. So thereby it must be true. Okay. All right. Treating the Higgs boson as a spherical cow. God. All right. So normal text. Again, there's going to be a lot more splaining to do. All right. So with the discovery. When was it again? It was Higgs boson discovery. It was 2012, right? It was like the 4th of July. Yeah, 4th of July 2012. Hold on. Wait, okay, so when did we turn it on and LHC? LHC malfunction. There we go. It's 2011. September 2008. Okay. So, so it kind of, this is what Professor Carroll said when he said it, quote unquote, blew up in 2008. Well, that makes sense because they would need to fix it. You're going to figure that's going to take at least a year or something like that. Then you need to get about 3 years worth of data to try to. Okay, that makes sense then. How fast are we? So sorry, I'm just randomly searching. 1, 2, 3, 4, 5, 6, 7, 8 digits. Okay. What would happen if the LHC? Well, that already kind of happened. Okay, sorry. All right. With the discovery of, yes, the Higgs boson or something that has attribute or properties. As properties similar to said boson, or something that's probably similar to said boson. Okay. The final piece of our standard model was experimentally verified. There we go. Yay. Happy words. All right. Confirmed. Verified. Okay, it's at least verified up to our precision. There we go. Okay. Why am I saying this here? Okay. Believed to be the one elementary scalar field that suffuses all of what of our realm. I'm just gonna, I don't know if there's something outside. Maybe there will be dragons. Sir fuses. Fuses. That suffuses all of our realm. I feel like that's a word. I feel like that's a word. All right. Let's put a star in front of that. I really want to use that word, but I should pay attention. There we go. That suffuses our realm. All right. Given recent measurements, we find the Higgs at the mass energy, find the Higgs to have a mass energy of 125 giga-electron volts. Okay. Where's the episode? We need to go back. I used it in a clip. Okay, let's actually just play that clip. Recycling content. It's irrelevant here. I swear, and this is just as an interlude. Okay. The but no ether video. God. Such a terrible person. Alright, let's play this. I also really just need the Mindscape episode. Selfish reasons. Okay. Alright. Do that. There we go. But no ether. Alright, I gotta unshare this. We'll go over here. Don't worry. Don't worry. I know. I know. This is not something anyone wants to do on a Friday night. Window crop tab. There we go. But no ether. Here we go. All right. Sure. All right. But no ether.
You finally flipped.
Well, I have a question, but it kind of backs up.
No, please.
When I think of the Higgs,
yeah,
it makes sense to me.
Oh, God, this isn't the episode I was looking for. Oh, this one.
Little cow here. No. No.
Hold on. I feel like. Oh, let me go back. Yes, I'm apparently worshipping an anime cow. Share screen. Boom. Higgs. Energy density balance. The cosmological. And apparently I accidentally spent like. I meant to spend $10 to boost it on Twitter/X or X Twitter, whatever. And I actually did it for 5 days. I'm like, I spent $50. I'm like, oh, you'll get like 2,000 to 3,000 maybe impressions. Well, yeah, it's at least like 50,000, 60,000 eyes were on. Now I realize I scroll past a lot of things and never even pay attention. But it was technically playing, so it depends on how you want to do its metrics. But I don't know. We'll see. Maybe it's in some folks' consciousness. It's just at least an idea. Here we go.
Little cow here.
Moo.
No. No. So if we take the vacuum energy density, we divide it by the spherical God Cow, we get approximately 1 point.
Okay. So I'm just terrible. I'm just going to go to Sean Carroll's. Because I actually need the citation now, because I'm trying to cite it. I'm just going to put the link to the exact timestamp. There we go.
I specifically and intentionally chose to be very different from each other in character. The spatial curvature is much smaller than it might have been. The cosmological constant is much smaller than it might have been. The mass of the Higgs boson, or equally well, the scale of electroweak symmetry breaking is much smaller than it might have been. The proton mass is much smaller than it might have been. The neutron to proton mass ratio is close to 1, but a little bit above, but not too much above or too much below, which seems a little fine-tuned. The entropy of the early universe is very tiny. The violation of CP in the strong interactions is very in the space of all possible theories that we haven't thought of yet. I don't know what explains why the cosmological constant is small, but it's a thought that said, look, in the space of all possible theories, we knew that it was 10 to the minus 120 or less times its natural value. And there was this school of thought that said, look, in the space of all possible
4806.
theories that we haven't thought of. There's this school of thought that 20 or less times its natural value.
There we go. All right, share. Then Professor John Carroll's. I don't know. I'm not sure if I should feel good or bad. It's just, I remember being taught like how you're supposed to cite things way back in the day before I forgot, and we have all these things that do it for us. But I'm like, sometimes it's like you have explanations that are so good. I'm like, in this lecture, I'm like, I mean, if you have a really good explanation and it's, why wouldn't I cite a video? It's, I mean, even Stephen Wolford's like, do people still do citations? Like, don't you just have links? Oh, blah, 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 blah. I'm like, again, I feel bad about saying that, but then, again, confirmation bias and appeal to authority. I think I just need to make this. Oh. We'll just fix that later. Okay.
And there was this school of thought that said, look, in the space of all possible theories that we haven't thought of yet, I don't know what explains why the cosmological constant is small, but it's easier for me to imagine a theory that sets the cosmological constant to exactly 0, even though I don't have that theory yet, than it is to imagine a theory that sets the cosmological constant to 10 to the minus 120, its natural value. I don't know how to do that, exactly the value that we haven't yet observed yet. But that's what it is. That's what it turned out to be. We were wrong, okay? So we were wrong. And when I say we, I include me literally, not just figuratively. It's not the royal we. I was there and I was wrong
That's why
about
I'm
this.
like, oh, somebody's saying they're
the
wrong?
cosmological constant is,
Sounds
or
good.
apparently
Sounds
looks
good
like 10 to the
science, in my
minus
opinion.
120, its natural value. So maybe it's not the cosmological constant that we're observing. Maybe the cosmological constant really is 0. Maybe we were right in some weird way, that there is some mechanism that we haven't yet invented that sets the vacuum energy equal to 0. And what we're seeing in the acceleration of the universe is some field that has an almost constant energy, but not quite, okay? Here's the problem with that idea. We would call this dynamical dark energy, or quintessence, sometimes it's called. The problem is the same as the problem with the hierarchy problem in the weak interactions. The Higgs boson field is a field that pervades all of space, and its mass is small compared to the Planck mass, right? Its mass is 10 to the minus 16, something like that, the Planck mass. And we say that's a small number. The masses in particle physics, under the rules of effective quantum field theory, tend to be big, tend to be driven up to very large numbers, okay? And so the hierarchy problem is just that there's a factor of 10 to the minus 16 between the Higgs mass and the Planck mass. If you have a dark energy field that is making the universe accelerate, it needs to be changing very slowly.
putting a picture
Otherwise,
of
we
the
would have
Minecast in
noticed
here
a
that
long
says-
time ago. If we were changing rapidly
it
on
also
cosmological
helps
scales,
make
that would have been
sure
easy
that-
to detect. It wouldn't even have acted like dark energy. The whole thing that dark energy needs to do is to change slowly so that its energy density is approximately constant and it can make the universe accelerate. So if it's an ordinary, not weirdly atypical field filling all of space that has some kind of mass, we talk about the mass of a field. What we really mean when we say that is the mass of the particle you would make by jiggling that field. That's what we mean when we talk about the mass of the Higgs field or something like that. It's the mass of the particle you would make.
Okay, so basically the produced particle from jiggling the field. So that's the mass there is the field strength. Okay. So I take that intuition and I'm like, let's turn the Higgs boson into a spherical cow. Why? Because I can divide by 4/3 pi r cubed. That much I remember after getting corrected so many times and doing things wrong. I am also happening to know that if you take the mass of a particle, you can divide that in with the speed of light to Planck's constant, the non-reduced version, and you get an associated Compton wavelength. So I just plug that in. It's literally the silliest thing in the world. But let's do that. Okay, so we can stop sharing this. Thank you, Professor Carroll. Let's share this window, our essay. Is that really in my notebook? No. Okay, that's my notebook. Yes, and I'm shilling Professor Carroll's Mindscape. Or at least it reminds me which link this is. All right. Okay, I need to make that a good bit smaller, I feel. If I'm gonna put the little thingy in there, yes. Okay. It's okay, we'll go through an editing process. It's all right. So in where are we? Inspired by this discussion. Podcast. There we go. Inspired by this podcast, the author decided to. I feel like this is exactly what I wrote on Patreon. I'm just going to copy that from Patreon later. Okay. Let's get into the calculation. All right. File, save as. Because we're actually going to do something. 36. All right. File, save to cloud. You gotta take care of the stuff and the things. I'm also starting to get a bit hungry. Because I say 36. All right. So let's do the calculation. Higgs mass. C squared. So it's in the mass energy. We're dividing by 4/3 pi r, where it's going to be its Higgs Compton wavelength cubed. Okay. Oh, enable dynamics there. Now I have to hit enter again. All right. Gives us this thing. It's, again, perhaps you can parse that. I don't know what it means. Looks like a really big number. Okay. Higgs boson mass. Okay, unit conversion, kilograms per meter per second squared. Okay. Is that on? Doesn't it have more? What's this other one? Same thing. All right. So 5 times 10 to the 42 kilograms. Well, you could express that as energy, or that's mass, that's energy. All right. I think it looks right. Content. About content. Pod content. All right. With that guy. Like that guy, roll it up, roll it up, roll it up. All right. Get this, move. All right, hide this somewhere here. I think it goes here, maybe. Yes. All right. It's basically the same thing. All right. Because it's an energy density. This. I feel like this should be indifferent. Oh, it's converting it. That's a mass energy. And then we're dividing. Ah, okay. Yeah. It's an energy density. It just doesn't say it straight up. Uh, this is why. Okay. And energy density. Because it's 4.9 times. Oh, that's all it's giving me. Get it. Undo. Roll you up. Times 10. Raise the was it 42 kilograms divided by meters seconds squared. All right. That should actually give us energy density or pressure. There we go. Stuff. Those are the actual dimensions. Yeah. When it only shows it in one way, you're like, oh, well, why do I need that? All right. It's yeah, because you got rid of the length squared in the numerator because you're dividing by 3 dimensions of length, which is a volume. So those go away, and yeah, and 1 meters goes downstairs. That's God. I feel like when did we learn about different things? It's like the denominator. It's like, oh, the thing downstairs there. All right. I don't even know. Oh God, it's all blending together. All right. So under pressure. All right, let's just delete this guy. All right, so now we have an energy density. Maybe we can cook with this a little bit. All right. All right. File. Save. Okay. All right, we have an energy density. So if that gives an energy density, let's take this whole dang expression. We'll view here. And then let's divide it into something else. And those magic words we type into Wolfram Alpha are universe energy density. So that's probably, I don't know, a good aggregation of stuff. Oh God, not available. Oh, sorry. Universe vacuum energy density. Okay, user error. I did the wrong words. All right. Gives us a dimensionless number. So 1.1 times 10 to the minus 52. Okay. Put that content out. Put content out. Okay. Roll it up. The little brackets are. Why does it need to be a list? There's no reason this needs to be a list. Sorry. Of course, it gives me an error. Under error. Oh, there's extra stuff here. Oops. That goes there. Deletes there. Maybe that'll work. Right? It worked. Oh my God. I don't know how to code, but I at least tweaked it. I delete like 3 things. Yay. Progress continues. All right, delete these guys. I know it's the most exciting thing in the world. NGU, Injure you there. Alright, roll you up. Okay, hidden away. All the Easter eggs. Alright, save. Alright, so we can start to wrap up now. Just with a comparison. Alright. This gives us an energy density. Okay. Need some words. If we take this energy density and divide it into the measured vacuum energy density of universe, we get a small quotations small number. There we go. File, save. Okay. So this small number looks this small. We get a small dimensionless number. Dimensionless number. This again. Small. Sure, any wrong. God. Small dimensionless number is of the looks a lot like the magnitude of the cosmological constant. I know, copy and paste. Copy and paste. Lambda. Oh yeah, that's the symbol I need. Okay, thank you, Wolfram Alpha. Okay. All right, so pod content. Okay, I. That's what it literally. Cosmological vacuum energy density length based proportional factor. Well, if we're gonna use vectors and convert everything to a length, that appears to be a length or reciprocal length squared. All right, I'll put all that stuff. That's the symbol we need. Thank you. All right, so let's reduce that, reduce that, reduce. I know I'm the laziest dude in the world. Oh, man. Lambda. There we go. All right. All right. So I think that's all I really want to do. I mean, what else are you gonna do? This is what it is. I need to go through and actually do the arguments, and there's actually a widespread if depending on if you're using like the 76 kilometer per kilo. I should probably actually do the whole dimensional thing and actually do the Hubble. I've been ignoring the Hubble constant. No, it's like, what is it, like 10 to the minus like 18, 19 reciprocal seconds or say, I don't know. Should probably dive into that and actually see. All I know is I'm pretty sure this probably matches a lot of the more CMB or the smaller and shorter scale stuff pretty well when you go by the higher things. Last time I think I did the calculation was like cosmological constant rather than 1.1 times 10 to the minus 50 was like 1.4 or a little bit more times 10 to the minus 52. So it got a lot bigger. It's like almost like 40, 50% bigger. So it's like, yeah. That seems to be a major difference. Now, again, why might that be the case? I could conjecture further. I'm just simply doing the most naive calculations in the world. It's probably something else, but I just find it interesting that if we turn the mass energy of the Higgs into a literal spherical cow, so to speak, if I divide by 4/3 pi r cubed, where r is its Compton wavelength, we get out a big energy density that, when divided into the measured vacuum energy density, and again, we can get a few more significant digits for that, but it comes out to be approximately 1.1 times 10 to the minus 52 in a dimensionless number. It just so happens to be about the magnitude and first couple of digits of the cosmological constant. Again, the cosmological constant has dimensions, our other number does not. But yeah, 1.1 times 10 to the minus 52 reciprocal meters squared. Don't that just beat all? Now again, could just be just random coincidence, but this Professor Carroll talked about things. He inspired me as a dreamer with a Mathematica notebook, and so that's how we got here. Well, that's about all. Going on for about 37 minutes. That seems like a good time. Save file, save as. Oh, jeez. Higgs, essay. Oh, 37. Hey. Maybe that's a lucky number or something. Perhaps we could use a 1 as well. Maybe 2 1s. Perhaps a reciprocal. Who knows? Alright, yeah, I know, it's very boring. But for prosperity, if Stephen Wolfram can go for like 6 hours just doing calculations, exploring things, I can go for 37 minutes. I'm not saying it was the most productive thing in the world, but oh, publish. So file, publish to cloud. So say 37. Publish. All right. So I will throw this in the chat. We should be good now. File quit. There we go. Throw this in the chat for anybody that's interested, and we shall throw in the link of the video on the YouTubes and stuff like that. So with that, take care of yourselves, everyone. Have an excellent weekend, and be safe, everybody. Let's hoping better stuff's around the corner. So peace out, everybody.